My name's Dave Van Hoy, and I'm with a company called Advanced Systems Group, and we're one of the contractors here on campus. And our primary responsibility here on campus is helping design and build facilities for the video production group, sometimes known as the Media Kitchen. And then we work quite a bit with the events production team and Jim Vastola, who will be speaking with me this afternoon, on the larger venues and recording and the integration of those types of facilities. My co-speaker today will be Brian Rutz, who's from a company called AJA. And AJA is a vendor to us and to Google, and they make all kinds of devices that help record and interface various types of video here at Google. But Brian is an excellent speaker and will be speaking on some of the topics regarding compression and formats and those types of things. And we even give him a little bit of credit because he's Canadian. So.
Back of the bus, I know.
All right. So what we're going to talk about today primarily is HD in consumer formats this morning. This afternoon we'll be doing a talk more about professional formats and acquisition and post-production. But what we want to concentrate on this morning is how does this affect at home? What am I doing if I want to see HD there or in a venue? And so we're going to cover some interesting topics like aspect ratios. Things like what does 16 by 9 versus 4 by 3 mean? Or what is progressive besides an insurance company? And what is interlacing? And things like GOPs, or GOPs as we call them. And then one of my favorites, which is, is plasma something you only get at the hospital? And of course, the last part is, what is an acronym? If you work at Google, you probably know that already. All right. So one of the things that's facing everybody at home is that digital transmission here in the United States is about to be not only a reality, but the only reality. That's going to be a very different world for a lot of people who have television sets sitting at home with rabbit's ears on them. For people who have cable boxes, they may not even notice. But for the people who actually do watch what we call terrestrial TV, it's going to be very different because the FCC has decided to finally repurpose what was the original analog television channels. So we're finding a lot of people are pretty interested in this because the world's going to look pretty different. Digital transmission in the United States, or terrestrial transmission as we call it, is a subset of the possibilities of things that can happen in high definition. These are the formats that are legal to broadcast over the air today and in February. And as a matter of fact, come February, a smaller set of this even. ATSC is the American Television Standards Committee, which replaced a committee that was disbanded roughly in 1961, which was called the NTSC, which was the National Television Standards Committee. Or in our industry, we usually call it the Never Twice the Same Color Committee. The HD in our world, for broadcast purposes, comes in two different pixel aspect ratios, 720 by 1280 and 1080 by 1920. Everything that we've known up to now has been in a raster size that's basically been what we've called 4:3, which is 480 pixels by 720 pixels, more or less. We also have different frame rates that are going to be affecting us in the ATSC standard than we've had. Up to now, all television in the United States that's been broadcast in any way, shape, or form has run at basically 30 frames per second. In fact, it's really 29.97 frames per second. But that's been the way it's been. The ATSC standard actually will give broadcasters the ability to, if they choose to, broadcast different frame rates for different types of looks and different types of reasons, including possibly controlling how much bandwidth they're using. Let's see here. All right, so how many of you have HD TVs at home and have seen this great thing where the picture goes wider and narrower, wider and narrower. And sometimes there's bars on the side. And this is the nasty transition point that we're going to be dealing with for a while between the aspect ratios that are part of the ATSC high definition standard versus what we have been used to, which has been a 4:3 standard. HD, when they designed it, was decided to make it more like the aspect ratios we're used to when we go to a film house or a more of a theater type experience. This has a lot of benefits from a production point of view, especially it means that as they shoot film or they shoot HD, it's a lot easier to repurpose material between seeing it in the theater and seeing it home. Up to now, we've dealt with a lot of what are called pan and scans. So you're watching a show at home on cable TV and it's 4:3, and you know that when you saw it in the theater, there was another character that was off to the side here that you're not seeing now. So the idea was to rationalize that and make it fit better. So all the HD formats that are legal under ATSC are 16:9 as an aspect ratio, and at a raster size of either what we call 1080, which is 1080 pixels by 1920 pixels, or they're 720, as we call it, which is 720 pixels by 1280 pixels. So this was to kind of illustrate what I was talking about with the issue of the 16:9 versus 4:3 and what we've been dealing with for as long as television has existed. So widescreen is typically 16:9, and in the aspect ratios I was talking about. One of the things that's really different and was taken into account during the ATSC design is that all of the formats today in broadcast HD are square pixel formats. And that was really done to line things up better with the computer world so that we would not have this issue of things looking wider and narrower and wider and narrower. Then in the older standard, everything was 720 by, well, we used to say 480, but it was really 486. It's just that 6 of the lines you don't see most of the time because they're overscanned. The pixels were non-square, which meant that if you drew something in Photoshop or then pulled it into a television application, like your any editing application, it looked strange and stretched. And then the other thing is, for a long time, we're still going to be dealing with this back and forth world. There's millions of hours of material in 4:3, and people are going to have wide screens. So how are we going to deal with that? How are we going to accommodate that? Is it going to be black bars down the side? There's what's called upconversion and scaling, which would take that image and scale it up, but now you have to crop the top and bottom, but I've filled the side to side, so it's a little more visually appealing, other than the fact that you might be missing the top of the character's head. And then we have the inverse of the problem that we've had all these years with 4:3 TV with film acquired assets, which was the pan and scan issue. So what they did to accommodate the fact that this character was off to the right when I'm in 4:3 mode is they would have literally moved the camera across the film that was turning this into video so that I could see the guy over here. Well, now we have sort of the opposite problem. When I scale that 4:3 material up to fill the bars on the side on 16:9, now I have to pan and scan up and down to make sure I'm not missing the tops of people's heads and things like that. So this is something that I think a lot of people don't realize when you talk about HD. It's really kind of a scary thing because HD is kind of like saying tires. All that tells you is it's a round thing that you might put air in. HD is almost as wide when we say those words. All of these formats that you see on here in some place are considered HD, with the exception of the very top line. And so that's a very confusing thing, especially if I go out to Best Buy and go buy myself an HD camera, and then I go shoot some stuff, and then I start downloading it on my computer, and then I want to play it back on the LCD in my living room. The results may not be what you expected. As a matter of fact, it may not even play on your television set because you might be out of raster from the formats it supports. And that's a very common problem. And you'll notice that some of these are kind of different aspect ratios as well. Some are, one right in the middle, the 1035 by 10 by 30, is 17 by 9 in an interlaced format. And we'll talk about interlaced and progressive in a moment. The point being that anytime you do anything in HD, you kind of got to know what you started with and what you're going to display it on, whether it's at your home or whether it's here at Google or whether it's in a professional application. Because there's no guarantee of what it's going to look like.
What is raster width and height on the LCD?
Depends on the LCD you buy.
Repeat the question.
Oh, I'm sorry. The question was, what is raster height and width on an LCD? It can be almost anything. There are LCDs that are 640 by 480 and LCDs that are 2048 by 1280. Again, you actually really have to look at the specification for the one you're thinking about buying. And one point that does bring up is that there are very few displays that you can buy today that are in fact really 1920 by 1080. Most of them are some other pixel aspect, quantity, hopefully in the right aspect ratio, because of manufacturing constraints. It's very difficult to manufacture a display that has that many pixels still. So most displays that you buy today that are HD are still not actually that many pixels. They'll be less. They'll be 1366 by 768 or 1280 by 720. It's only the ones that actually have 1920 by 1080 that are what we call pixel for pixel. Does that answer the question?
No, you had raster width and height on the previous slide. What are some of
I'm sorry, let me go back here.
Yes, so you're saying that I need a 2750 by 1125 LCD to view the last format? Or what is there?
No. To view the last format in its native resolution, you would need a 1920 by 1080 display to see the full resolution. Pixels versus raster width are slightly different. It's confusing, isn't it? And it's different than in the computer world because you're scanning every frame. I'm going to let Brian, do you want to?
That's kind of, if that's advanced, maybe this afternoon is better.
Yeah, it is something we're going to cover this afternoon. Okay, so one of the big differences as we move to the new world of digital television is that everything, the old system was all analog. Signals moved from place to place as completely analog channels all the way from where they were acquired to how they were recorded to how they were played out over air. When we move to the world of HD in particular, but anything that's DV or any digital video in any way, we have a process that has to go on to be able to record it. We have an original sensor, and the sensor in every camera today is analog, which most people don't know. And then it goes through a process called sampling and quantization, which is taking little samples of the analog information, then taking and recording those at a certain rate. For all of the formats that are digital video today, that creates more data than we know how to record in any physical mediums today other than directly to a hard drive array. So the last step almost always includes some compression codec. And we'll talk about compression codecs in the sense of consumer delivery in Brian's part of the talk. Okay, how many of you have heard the terms of 1080p? Seems to be the thing that everybody puts into their Best Buy ad or their radio commercials. 1080p. So what is progressive versus interlaced? All video up to now in standard def that you've seen in broadcast has been in an interlaced format. Progressive frames are where the entire frame is captured or played out at once. In an interlaced frame, they alternate. This was done effectively as a compression method in analog TV. And if you look at the composited frame at the bottom row at a 30th of a second, that's in fact what actually is played out. But your eye doesn't perceive that. Your eye sees it put back together. Yes. So the reasons for using interlacing are that it reduces bandwidth. The reason to use progressive is it improves vertical resolution. Probably most people here don't remember when we actually had interlaced displays on computers, but let's just say moving to progressive was a very nice lead into where we have graphics that we can actually see today on screen. Progressive has less motion artifacts. Progressive reduces compression artifacts, which when Brian gets to talking about MPEG will be pretty apparent. And progressive to interlace conversion is easy, whereas interlace to progressive is not so easy. Now this comes back to both what you'll see in broadcast today. One of the slides I didn't put up that I should have was the world of broadcast TV today is split between progressive and interlace formats. As you saw on that table, both are possible. So some of the major networks, such as ABC and Fox, have chosen to go with progressive formats. Others, such as CBS and NBC, have chosen to go with interlace formats. And that has to do with how they want to use the bandwidth that's available to them. And I think that's one of the biggest differences that we see as we think about delivery of television to homes today, that there is, it's all about bandwidth. And as you start to look at terrestrial TV, you'll find out pretty soon that most of these stations have the option of broadcasting multiple channels simultaneously now. So they're going to choose what their broadcast main format is in order to save bandwidth, so they might be able to run 2 or 3 channels at the same time. Now, up to now, we've talked mostly about what's ATSC formats, which are what are legal for broadcast and what are required by the FCC. The other part of consumer HD today is what we call non-broadcast, or things that wouldn't necessarily be legal to run out over the air. That we've been experiencing for some time if anybody's got a DVD player at home. Most of the formats that are on DVDs that you rent at Blockbuster or through Netflix would not be broadcast legal. They're in fact encoded progressively. The DVD player has the option to play it out with interlace. But if you try to put that directly up on a television transmitter, you'd have a problem. And then we've continued that tradition as we move forward into the wonderful world of high def. So what kinds of things would we have at home that might be not broadcast legal? Well, we have Blu-ray discs. Finally, we have a resolution in the high def DVD war. Blu-ray discs can contain many, many, many different formats. And virtually none of them are broadcast legal except for the few that you saw on the table. We have what's called DBS, or direct broadcast satellite, which would be things like DirecTV or Dish. We have on-demand over cable, because there's no requirement for the cable companies to do anything that's ATSC legal. We have on-demand over the internet, and we have internet streaming, all of which can provide high-definition formats that wouldn't necessarily be broadcastable.
What are the data rates? Each of those?
The data rates are actually not locked to any of those. So in other words, you could do any of those at data rates that range anywhere from 10 megabits a second up. But in sort of a general way, Blu-ray discs are generally going to be in the realm of 20 megabits a second. ATSC is around 20. Most of the DBS people today are varying, depending on their programming, between 12 and 20 megabits per second per channel. I'm sorry, I didn't repeat the question. The question was, what kind of data rates are these different types? So, and of course, internet streaming could be as big as your pipe. So why? Why did we end up with this again? Especially after spending all this time trying to, it took the ATSC committee over 10 years to come up with the standard that we're rolling out. And that's because broadcast formats are constrained because they're meant to work at a certain point in time. You sort of have to stick a stake in the ground and say, this is where we are, we can make things that work here today, and this is what we're going to do going forward. The world of non-broadcast doesn't have to do that. They can move at any rate that deployed technology feels like going. They don't need to adhere to standards that are regulated by the government necessarily. So this is one of my favorite slides that I know you can't read. And for anybody who would like this PDF, I'll hand it off so that it can be posted with the presentation. It's from a vendor called Miranda. But I wanted to give you a sense for how unbelievably flexible and complicated television is today. That in the middle are all of the possible aspect ratios and conversions that every television station has to deal with today. On the bottom left are the plethora of formats and their data rates. And up on the right are various codecs and their compression schemes. And then in the upper left are all of the possible rasters that exist today that are currently in production someplace. And this is completely different from the days of when we had NTSC television here, where that entire poster would have been less than one box of this. Question in the back.
Is that just America or is that worldwide?
That is worldwide. But in America, it encompasses roughly 3/4 of that. The question was, is this just in America or worldwide? All right, so I wanted to talk a little bit about different display technologies, and this is sort of a 50,000-foot view. But we get questions all the time about various display technologies that can be used to do HD. The big ones that everybody sees today are plasma, LCD, and projection. And they each have advantages and disadvantages. So plasma was one of the first really widely available HD formats. What the big advantage of it is that it's extremely bright. It has very low motion artifacts. It has very low latency because of the way the display actually is built. And that it's easier to achieve what in the consumer world is black ratios. If you look at different kinds of displays and you'll see in the shadows where you think something ought to be black and it's gray, that's what they typically talk about when they say 3,000 to 1 black ratio. Well, that's the ratio between the brightest pixel and off that's displayed in theory. And so because a plasma is not backlit and doesn't have a filter effectively, when it's off, it's off. Now, the downside to plasmas are that because they're a large gas-charged tube, they use quite a bit of energy. If you leave an image up on them for a long time, they will tend to burn in the way CRTs used to burn in, which we've kind of learned to not have to deal with. And they don't come in a very wide variety of sizes, although some of them are pretty amazing. They don't get very small, but plasmas get very, very large. There are plasmas today, I think the largest one that's currently shipping is 108 inches diagonally, and they've announced 153. I can't imagine what it weighs, but LCDs. We see lots and lots of LCDs. Everybody who has a laptop in this room right now has an LCD. LCDs can be made to very high resolution. The energy consumption is very low. Generally, they're backlit with either fluorescent tubes, or we're beginning to see LED backlit, which gives us better color imaging. They don't have burn-in issues because of that. And because of the type of technology, they can be made very small. We've all got them on our cell phones. They use, now the downside is that because of the latency of the pixels and how an LCD changes its color, they tend to have more motion artifacts. So for instance, if you go to the big box TV store and you're watching a soccer game and you watch closely, you'll see on most of the LCD TVs, you'll see some amount of image smear. If you look at the plasmas, you won't see that. And that's because of the amount of time it takes for a pixel to turn from on to off or off to on in LCD technology. Also, LCDs are effectively a filter. When you look at an LCD, you've got a light behind it and you've got the display in front of it. So how dark an off can be or black can be is a very tricky thing in an LCD. So they tend to not display blacks as well as plasmas, especially on very large screens. And then we have projection displays. Projection displays are kind of a mishmash because they internally have a lot of different technologies that they use. Like for instance, the one you're watching right now uses a technology called DLP. And DLP uses these little tiny microscopic mirrors to focus the light. But there are also LCDs that go in projectors, and there are also beginning to be what's called LCOS, which is liquid crystal on silicon displays. The nice thing about projectors is that they're designed to make very large images. So if I want to have a home theater at home and I want to have big theater type experience, projectors are really nice. They can be very high resolution because of the types of designs and the fact that they can use processing on the image displays. And generally, they're not subject to burn-in, not in today's world. On the other hand, as anybody who's sitting directly below that projector knows, it makes some energy. You might even be able to feel the heat come off of it, or uses energy. They can be noisy. They have to be cooled because you've got a very bright light source. And they have the highest cost to maintain because you use high energy lamps that degrade over time and eventually burn out. So projection has that cost as a trade-off. So which one works best for you is always a question for your venue and your personal tastes. The last part I wanted to talk about before I have Brian talk about HD acquisition, what happens if I go buy a camcorder today, was how does this stuff get interconnected? In the old days, we had composite video, and we had one wire went from here to there, and it carried the whole signal. To do high def requires, at a minimum, that we have an analog component connection. There is no composite multiplex together HD signal today, other than if I'm running it in a broadcast format. And you can transmit audio over an analog format. And I didn't cover audio a great deal in here, but that's really for another day. But suffice it to say that all of the HD formats are capable of carrying multi-channel audio in the same way you're used to with your DVDs. The primary ways of moving HD today in the consumer world are either DVI or what's called HDMI, which are the digital interconnects that we see on almost every display today. And DVI is, of course, very prevalent on computers. Part of the reason for moving to digital interconnects was for quality, to be able to move things without the degradation of analog transmission. But the other reason that was a much bigger motivator for the content producers was copy protection. And this will come up a lot as you look at things that you would buy for home and this concept of what's called HDCP. HDCP is the high bandwidth digital content protection specification. It was originally from Intel. It's what we call a DRM, or a digital rights management scheme. It can be incredibly infuriating to deal with, and I would recommend that as you look at things to use in your deployment of HD, you be very, very aware of HDCP. In the design of this room, HDCP became a very big issue. In order to keep piracy down, everything that is broadcast digitally today has DRM built into it, whether it's coming over the air, whether it's coming off a Blu-ray disc, whether it's coming through your DirecTV setup. And this allows the content rights owner to control what you can do with it. Can I record it? What kind of display can it be played on? Can I duplicate it? If I've recorded it, can I make more than one copy? And this is built into Blu-ray players, it's built into your Comcast box, and it can really be a problem. Especially the one that you run into most often is you go out and you buy a projector and it's only got an analog set of inputs. I hook it up to my friendly Blu-ray player and all I can see is 480 standard def. Now I can see it in progressive, but I can't see it beyond that. And why is that? It's because of the fact that they have limited that Blu-ray disc so that it will only show high definition output on a legal display. So you cannot make a copy of it. They know that analog is easy to capture. These digitally controlled formats are almost impossible. And so this is something that I really want to caution everybody about. It's something to pay attention to. It's easy to go buy a TV or a display, get it home, and find out very quickly that you can't get from here to there, or my AV receiver that I wanted to use only has component analog through it. And all of a sudden you're like, oh, I have to buy a new receiver? These are major issues, but they're done to protect the rights holders, because piracy is a major, major issue. Question here.
I have a question about the plasma displays. Do they still have the brightness issue, where over time they get
They degraded?
Yeah.
Not as much, but yes, it is it's a charged particle environment, and over time they will degrade. We're seeing much less of it now than we used to, and generally some other part of the plasma fails before the display itself does any longer, like the power supply or something like that. But yes, it's part of the physics of the display. But they have improved it a lot, along with the burn-in issue. And they deal with the burn-in issue now by having DSP watch what's going on any given pixel, and if it stays there too long, they move them adjacently back and forth a couple of pixels to keep it from burning.
I was wondering about LED technology. Will there be, will they be making LED monitors as opposed to LCD, or is that?
LED displays exist already, and when you see them, when you go to large venues, like if you were to go to, I was going to say Pac Bell Park, but I guess this week it's AT&T Park, and you looked at that very large HD display, that's using very, very large LEDs, actually. So a lot of digital signage that's very large is LEDs. We don't see LEDs yet in any consumer displays other than for backlighting LCDs, although it is being highly touted as probably one of the next technologies to come, particularly a format called OLED, which means organic LED. Any other questions? And I'm going to turn it over to Brian Rutz. And Brian's going to speak to you on codecs and compression schemes and how things relate in that part of the world.
It worked.
Yay. Amazing.
Thank you.
Good morning still, everybody. Thanks, Dave. Everybody wide awake? Because I don't take prisoners. Never have, never will. So we're going to condense something, dramatically condense it down from what we normally do on these kind of presentations, but it's an idea to give you an idea of just what the heck's going on. I don't know. I've only worked in television for 40 years. I have no idea what's going on now. Can you imagine 40 years? My first experience with nonlinear editing was actually cutting and splicing quad tape while I was going to, that's 2-inch wide, by the way, tape while I was going to college. Okay, Dave has referred to the interlace and progressive thing. Just to remind you, progressive is a full picture every time. The entire resolution you see in each frame as you look at it. Interlace, as Dave mentioned, was a form of compression so that we could incorporate color. And a guy 100 years ago was at an SMPTE in New York, and a guy defined NTSC, color, never twice the same color. He described it as buying a one-bedroom condo on Central Park West in New York and finding out your mother-in-law is moving in permanently. And we had to accommodate color on our existing television system. And that's what they did, created this whole interlace way of doing it. In Britain, they did basically what we're doing now for next year and saying your TV set isn't going to work. You got to get one of these new ones when they went to color because it was an entirely different standard. Interlace versus progressive scan. As Dave said, we'll just go, you can read that faster than I can. So that's why we like progressive. So we have frame-bound and non-frame-bound compression. And I see that calf staring at a new gate look all over the place in here. What's he talking about now? All right. Frame-bound compression means we address each frame individually. And we hear terms like 411, that's DV, we have 420, that's HDV, 422 and 444, and even 4444 at the very high end. What we're looking at is a ratio. The first number refers to the luminance samples. That's the brightness and darkness and the most important part of our picture. That's where our detail is. The color is just window dressing, okay? So in this particular case, for every 4 samples of the luminance video, we have 1 each of the red and blue information. Because in television, television has to have that luminance information. RGB doesn't have that, so we don't record RGB in television. Because this is a subtractive process, if we were to add the luminance, which is the letter Y designation, if we added that up, we'd have RGB. Everybody got that? Correct response is a nod of the head and a yes, Brian. All right. So what the heck does that mean? So this, imagine, if you will, we're looking at a CRT here. I guess it could be an LCD or a plasma, but we're looking at the extreme magnification of the upper left-hand corner. Okay? So each one of these black squares represents a picture element or pixel. So in the first pixel, and every pixel thereafter, we look at the luminance information. There's our 4 luminance samples. Everybody got that? Good, good, okay, good. Some of you are awake. So in the first pixel, we sample the red information and the blue information. And that's the way we sample the color. So you can see that the color information is shared across 4 pixels. That, in a way, is a form of compression because we're reducing the amount of signal information we have. And 420, this is when JVC introduced the HDV format. How many years ago was that, Dave? 4, maybe? 4 or 5. They used a 420 sampling structure, which is the same as DV is in the PAL standard countries, like Europe or England primarily, and all over the rest of the world. So this is how we did that. We have the same amount of color, but the color information comes from 2 different pixels. To our eyes, we see no different. We see no difference whatsoever. All right. So, MPEG2. We've heard that a lot, right? MPEG2. MPEG2 is not one thing. Dave referred to saying tire. I refer to saying car. That's what MPEG2 is. And basically, when you go to the mechanics, you're going to get your car worked on. What does he do? He wheels up this great, huge red toolbox, right? You've all seen those things? And he starts opening doors, and he starts pulling out drawers and mixing around, looking in there. That's what MPEG2 is. MPEG2 is a number of profiles and levels that can be mixed and matched and twisted and turned and screwed up really badly. And that's what it is. It's an editor's, it's a developer's dream. For those of us in television, it could be a nightmare. Anyway, so it's interframe compression. I'm going to explain that. And the profiles and levels, that's the permutations and combinations that can be done there. And we call it a group of pictures, or GOP. We have three components to that. An iframe. The iframe is everything we know about that picture is in there. okay? Then we have B frames, which are generally bidirectional comparators. They look back and forth. And the P frames predict what's going to change. So basically, all the information is in the I frame. What is in the P and the B frames is only information having to do with that which changes. Okay, so that's an extremely efficient way to transmit a signal and to record a signal. And there are, as you see in the bottom, there are transport and program streams in HDV. So if we look at the original HDV, which was 720/30p, it had a group of pictures of 6. That's still considered a long GOP structure. So we had an I frame followed by 2 B frames, a P frame, 2 B frames, and an I frame. Transmission has been using MPEG2 for quite some time now because it's, again, very efficient to take up less bandwidth on a satellite. And I was watching for about the 7 millionth time John Wayne in Rio Grande. And John Wayne was walking across the jail, and it was a 3/4 shot of the jail. And he walked from right to left across the frame, and Scotty was having trouble beaming him up because he was all pixelated. There was something wrong with the transporter beam at that particular time. The floor was fine, the walls, the ceiling, everything else was great.
John Wayne beaming out?
Yeah, in Rio Grande, taking place in, what, 1860? That's what it looked like. It looked like, because you know how in Star Trek they went all that pixel thing when they slid the sliders up, made of wood, which was kind of interesting. And that's what was happening. The MPEG2 encoder, the MPEG encoder they were using at that moment, had a hiccup. And because there was so much still data in that picture, the moving data got screwed up. All right, so, yeah, isn't that great? Now, after JVC introduced the 720p version, 30p version of HDV, the interlaced version of HDV came out, and that's used by Sony and Canon. And they used a longer group of pictures, because it's interlaced, a group of pictures of 15. So you can see, or you start to get an idea, if I want to edit here, there's not enough information there for me to commit my edit, is there? There's only some data having to do with things that move. I can edit on an iframe, no trouble at all. But I don't want to edit on an iframe. Plus or minus 15 frames editing accuracy is totally unacceptable. Plus or minus 1 frame is totally unacceptable. So what do we do? If I want to edit here, that's where I, as an editor, have made my choice that I want to edit. And remember, I'm editing in the codec, encode, decode, the HDV codec in this particular case. So I say, okay, that's where I want to edit. So now I turn the CPU loose to reconstitute that entire group of pictures to give me 15 video frames. Now, this is obviously a whole lot slower than what it would be, but one of the most common complaints we get from people saying, oh, you know, I'm editing HDV or I'm editing H.264 or whatever, and it's taking so cotton picking long. Well, they're editing in the codec, which is one of the reasons at AJA, all our cards have no FireWire connection. You come in HD SDI, high def component analog, SDI, in a real baseband video signal. Because then everything's in iframes when it goes in. And you can edit anywhere you want, and the drudgery of waiting for all this to happen has already been done for you. There are other ways the manufacturers compress things. For example, this particular version of HDV actually records 1440 by 1080 pixels, not 1920 by 1080, 1440 by 1080. And then on playback, subsampling brings it back up to 1920 by 1080. Digital magic, right? Digital magic. Panasonic with their DVC Pro 100 or DVC Pro HD, they actually record 1280 by 1080, subsample on playback to bring it up to 1920 by 1080. So it's all this magic going on. I'm a big fan of progressive scan, by the way, as long as it's 60 frames. So we talk about film. I love film guys, particularly graduates of a film college, because they're buzzed with the beauty of film, and there's no question about it. Film has a number of wonderful and amazing attributes. I don't believe 24 frames per second is one of them, because the image jerks, because we're only seeing 24 pictures every second. When we watch NTSC today, we're seeing 60 pictures every second, albeit half res. So if you can get that progressive scan image, all those images, to a faster data rate, so we got seeing more pictures. 30 frames has a lot of motion jitter in it. So if the camera isn't moving, it's fine. It's interesting that when we go to the movie theater, very often the movie is being projected at double flashed at 48 frames a second or even 72 to reduce the motion jitter we see with our eyes. So for years, we used to have this big thing called a telecine, and it was great fun because when you change it from one projector to another, you could hear it all over the building. Oh, got a question over there. Sorry, go ahead.
About double flashing, is that going to be changing anytime soon?
About that what, I'm sorry?
Double flashing in theaters? With the
when we go to digital television, probably, or
Right,
digital cinema.
Right, I know, but I mean, for years and years and years, we go to the movie and they have these really slow pans because they don't want our eyes to go crazy.
Yeah,
And I'm
exactly.
just wondering if they're actually going to be fixing that with all the new
It's hard to
technology.
say. There's always going to be the purists that are going to want to shoot on film. They're not going to want to shoot digitally. I would be the last person on the planet to say video is going to replace film. That's one of those arguments you never want to get into, like religion and politics. I've been a video guy all my life, so the last time I shot film was with a Bolex in college. I tell people I've worked in television longer than the invention of electricity when you had to watch TV by candlelight. So what we did in order to get, you've heard the term 3-2 pull down. This is a very simple diagram of how that works. We take one film frame, and the first one goes to 2 fields in an interlaced video signal. The second frame goes to 3 fields, then 2 fields, then 3 fields, hence 3-2 pull down. Everybody got that?
Yeah.
Good, okay. So what Sony does in the field is they capture, the camera sees at 24 frames per second, they record to a hard drive, to tape, whatever, mostly hard drive, in 2 fields. So they do what's called progressive segmented frame. Progressive segmented frame. That's a way of getting progressive into an interlaced look. So that's just what they do. And Panasonic has another way of doing it. They call it Varicam recording. And what they do is they record at 60 frames progressive scan and flag the appropriate frames digitally so that when it plays back, we see it as a 24 frame playback. Variations on a theme. Okay, so formats, we'll go through this really quickly because this is mostly very high-end stuff. We've got, from Thomson Viper, this is 444. You remember from the beginning, we got 4 luminance samples for R minus Y, for B minus Y. It's a huge amount of data. Has to record to a hard drive. And this would be largely to go to a film out, go into a digital intermediate in the post-production process, and then printing to film at the end, or going to digital cinema, which is coming on like gangbusters. This is a Sony version of 444 in their HDCam format. Panasonic's HD422. These are coming down in prices. We're going along here, but none of this comes into the, they're probably worth more than my house these days. And the HDCam format, which is very popular. There's all kinds of people using HDCam for acquisition. Now we talk about compression. Way back when compression, when I first heard the word compression, I said, well, what the hell does that mean? This has got to be in the early 90s, I guess. And guys say, well, if you take a piece of paper and you fold it in half, You fold it in half again, you fold it in half again, you fold it in half again, it'll fit in your pocket. So we've compressed that piece of paper down so it'll fit in the back pocket. Now when we unfold that piece of paper, is it exactly the same as it was when it went in there? No, because it's now got wrinkles in it. I thought that was a pretty apropos way of describing compression. We have now got so many different codecs and ways of making it much, much cleaner that it becomes virtually transparent. HDV editing in the codec. You can, but then we get into that group of picture structure we talked about. Excuse me. So uncompressed or an intermediate codec, there's, name escapes me, Dave, the codec company. Down in Southern California, it doesn't matter. Anyway, they developed a codec that you could feed HDV into and then edit in that codec, an intermediate codec, or you could use Apple's ProRes 422 codec or DVC Pro 100 codec or whatever the case may be. So that's pretty much it. Do you have any questions on this? I know we've gone through this at that extremely fast rate, but it just gives you an idea of the choices we have, and all to get us to ATSC. Okay?
All right.
Thank you for your attention.
Okay, thanks. The